Same thing. I've just gone ahead and run this. I just renamed BMI, lowercase BMI, made it a factor. It's easier to type. Systolic, I just made it lowercase, easier to type. And I had to force age as a factor. I really didn't even need to do this because I'm not going to use BMI in this example. So let's check the assumptions. To run Levine, I have to install CAR. So I run the Shapiro test for normality, for systolic blood pressure. I have statistical significance telling me I have a violation of the normality assumption. I run Levine's test to check the equal variances. I want to keep median there because I'm diving into the non-parametric world. Non-parametric world is all about medians, not means. I have statistical significance, so I do not have equal variance for systolic blood pressure across age groups. So I have a violation of equal variances. Calculated my sample size. Now again, with a sample size of 300, if I was going to publish this where it really, really mattered, I would just go ahead and proceed with the standard one-way ANOVA, a parametric test, because of my sample size. However, let's say you present something like that to a referee journal and they kick back your article and tell you, nah, you're using parametric tests when you need to be using non-parametric tests. So what would you do? Well, you would shift gears and focus on a Kruskal-Wallis test. So focus becomes on the median, focus becomes on IQR, and focus becomes on quartiles, and don't really pay much attention to the means for these tests. Create my ranks. So I rank systolic blood pressure, and all the systolic blood pressures get a new rank. And I created a new data set here by doing something called a data frame. And so all these things now have a rank. It really there's 300 of them. I don't want to show you the whole data set, but you can see that this will rank the data in terms of the systolic blood pressure. You can see that the 98 is lower than the 106, so it's got a lower rank. And the 0.5 is just, for ties. So then my focus becomes on the sum of the ranks. So comparing 20,600 to 12,000, it looks like to me that there is going to be a significant difference in the sum of the ranks for this comparison. Fortunately for you, you don't have to worry about that. To run a Kruskal-Wallis test, just type Kruskal.test. This is your dependent variable. This is your independent variable. I didn't want to take any chances, so I let data equal new data to make sure that it is taking the data from the new data. All right, so same difference. I have a p-value that is statistically significant, so I can conclude that my medians aren't equal, right? So at least one pair of medians is different. So because of that, significant result should, you should be on autopilot now. When you have ANOVAs, whether it's parametric or non-parametric, when you have a statistically significant result, you dive into post-hocs. And the way a post-hoc is run with R, after a Kruskal-Wallis, a significant Kruskal-Wallis, is to use the pairwise.wilcox.test command and use the p-adjust method BH. I won't even go into what that's about. It's just one method that controls for inflated type 1 error rates. Compare pairwise, we see that all these values are less than 0.05, so pairwise, all three are statistically significant. And we can conclude different median systolic blood pressures across all pairwise age comparison. So 18 to 39 compared to 40 to 64, we have statistical significance. 65 and older to 18 and 39, we have statistical significance, and so on. So I think inquiring minds at this stage probably would want to know what if we just gone ahead and run a parametric test? How would it have worked out? The same. You have a lower p-value than you have up here. Not much. It's so small. In both cases, you're still rejecting the null. Over here, it would be that the mean of the 18 to 39 is equal to the mean of the 40 to 64 equal to the mean of 65 plus. So we would reject that, and we would run a two-key post hoc, and notice that pairwise all are statistically significant. So there are cases, though, because even though this p-value right here is larger than that p-value right there, again, both are statistically significant at the 0.001 level, but there are cases out there, situations out there that you could imagine where maybe a p-value here turned out to be 0.06 and a p-value down here turned out to be 0.04. So you're in the statistically significant world versus the non-statistically significant world, and that kind of stuff can happen. But you must have your analysis grounded in appropriate theory to proceed. All right, let's check it out in StatCrunch. I don't like StatCrunch for non-parametric, although it works. So let's run a Kruskal-Wallis. I'll tell you what, let me scoot this over here. I want you to be able to see the results. So let's where are we here? Okay, I want you to concentrate on this right here. All right. So we will have values systolic. We want to look at age, and I want to adjust for ties. Okay. So you can see we get the same thing. Degrees of freedom 2. Chi-square statistic is 58.32, which we get right here, and the p-value the same. One thing I do like about StatCrunch is it provides the summary stats. It gives us the median and the average ranks for each of the age groups, and it gives us the sample size, which is considered in the calculations. Unfortunately, at least I can't find out how to run a post hoc for a non-parametric test in StatCrunch. I could clearly run multiple non-parametric t-tests, but that doesn't adjust for the inflated type 1 error rate. So anyway, I'm not going to we're not going to go too deep into the weeds on non-parametric stuff, but again, I want you to have it on your radar because it does. There are situations in health sciences where you need to use it. All right, take care.